Assalamu alaikum. In this lecture, we are going to solve a tutorial related to the long transmission line, in which we have to find the phase constant, surge impedance loading, velocity of propagation, and line wavelength, as well as the sending end and receiving end quantities of the transmission line.
A transmission line is given to us, which is 500 kilovolt transmission line. The length of the line is 300 kilometer. The inductance is 0.97 millihenry per kilometer per phase, and the capacitance is 0.0115 microfarad per kilometer per phase. So now what we have to do, we have to consider the line as a lossless one, and we have to find in the first part the phase constant, which is beta, then surge impedance Zc, velocity of propagation V, and the line wavelength. Then in the second part, we have to find the sending end quantities. And what are the sending end quantities? These are the source voltage and source current. Later we have to find the voltage regulation, and for the calculation of these two, sending end quantities and voltage regulation, we are given with the receiving end voltage 500 kilovolt, rated load that is 800 megawatt, and the power factor that is 0.8 lagging. So now we are going to start the solution of the example. So first we have to find the beta, that is phase constant. So for lossless line, beta is equal to omega under root LC, inductance, capacitance, and omega is equal to 2 pi f, where f is equal to 60 hertz. So all the values are given to us. So we just have to replace it with the values. 2 pi into 60 under root 0.97 into 10 raised to minus 3 into 0.0115 into 10 raised to minus 9. So the beta value will come out to be 0.001259 radian per kilometer, because these values, both of them are per kilometer per phase. So the phase constant value is radian per kilometer, because if you remember in the lecture when I was explaining the phase constant and the attenuation constant, so the values were radian per unit length. So in this case the unit length is kilometer, so I am taking beta is equal to radian per kilometer. But if you will take the whole length of the line, so this kilometer will not be present in the denominator of the unit, and the phase constant will show you the phase difference between the sending end voltage and the receiving end voltage. But in this case it is just the phase difference between the one segment and the other segment, and the each segment length is 1 kilometer. Now the second thing, this was the first value that we have to find. The second value, we have to find the surge impedance. The formula for surge impedance is under root L over C. Again, we know the values for inductance and capacitance, which is 0.97 into 10 raised to minus 3 and 0.0115 into 10 raised to minus 9. So after putting these values, it will give you 290.543 ohm. This is not characteristic impedance, or we can replace it with Z0. So this is your surge impedance, because this is the impedance of a lossless line. So the characteristic impedance of a lossless line is known as surge impedance. So you can also write it as Z0. It would be easier to remember. This is your surge impedance. The third quantity that we have to find is velocity of propagation. So velocity of propagation V is actually equal to 1 over under root LC. Again, you know the value of inductance and capacitance. So the velocity of propagation will come out to be 2.994 into 10 raised to 5 kilometer per second. And the last thing that you have to find is line wavelength, which is lambda. And if you remember that lambda is equal to V over F, the value of V is 1 over under root LC. So the final formula will become F over under root LC. We know the value of frequency, that is 60, value of inductance and capacitance are also known. So the wavelength will be lambda is equal to 4990 kilometer. So this was the first part of the example, the numerical. In the first part, we have to find the phase constant, surge impedance, velocity of propagation, and line wavelength. So we have calculated all those 4 quantities. So now in the second part of the example, we are going to find the sending end quantities and voltage regulation. So for the sending end quantities, we know the equations for the sending end voltage and sending end current, sending end quantities. So we know the equations for sending end voltage. It is cos beta L receiving end voltage plus J ZC sine beta L I R. So this is the sending end voltage for the lossless line, and for the sending end current it is J I over ZC sine beta L V R plus cos beta L I R. So these are the sending end voltage and current equations for the lossless line. So these are found by putting the gamma, which is the propagation constant, equal to beta j, because we are taking alpha is equal to 0. So for the lossless line, the sending end voltage and sending end current are these 2 equations. So now we have to find beta L. We don't know the current IR, and also we don't know the phase receiving end voltage. So we will start from the beta L. So we already know the value of phase constant that we calculated in the previous part of the example. So it was 0.001259 into the length of the line, which is 300. So it will be 0.377 radian. So the unit of this was radian per kilometer. This is kilometer. So beta length is beta into L is equal to 0.377 radian. So now this value is in radian. If I have to convert it into degree, so beta L will be equal to 180 by pi into 0.377 radian, and it will be 21.641 degree. For the receiving end voltage, VR, the value that is given to us in the example, in the values, the value that is given to us is a line-to-line voltage. Now we have to convert it into a phase voltage. So it is 500 angle 0, which is the receiving end voltage divided by under root 3. So that will be 288.675 angle 0 kilovolt. So this is your receiving end voltage. Now for the receiving end current, IR, we also don't know that in this equation. So to calculate that, we know the load power. So that is actually equal to 3 VR IR cos theta. So if I have to calculate IR, that is equal to P load over 3 VR cos theta. We know the value of P load, that is 800 into 10 raised to 6. The value of VR, it is 288.675, 288.675, and the cos theta, it is actually equal to 0.8, and this is kilovolt. So the IR value, that will be 1154.701. But this current is actually the magnitude only. We also want to find the phase. Now for phase value, we know that cos theta is 0.8, theta will be 36.87. But as the power factor is lagging, right? So this theta will be negative for the current, minus 36.87. So the IR will be equal to 1154.7 angle minus 36.87 ampere. So now we have calculated the beta L, then we calculated the phase voltage, phase receiving end voltage, and then we calculated the receiving end current. So now for calculating the sending end voltage and sending end current, we only have to put the values of all these quantities. So Vs is equal to cos beta L VR plus JZC sin beta L IR. So we know IR, beta L, ZC, VR and beta L. So the Vs final value will be 356.53 angle 16.1 kilovolt. Similarly for Is, it is equal to J1 over ZC sin beta L VR plus cos beta L IR. Again we know the characteristic impedance beta L, receiving end voltage beta L and IR, so all the values are known. So the sending end current will be Is is equal to 902.3 angle minus 17.9 ampere. Now we also have to find the sending end power. So we have three quantities at the sending end: the sending end voltage, sending end current and the sending end power. And the formula for the sending end power is S3Vs Is conjugate, right? So we know the value of Vs, we know the value of Is, we have to take the conjugate. By conjugate we mean that this sign will become positive, and the final value for the sending end power will be 965.1 angle 34 MVA. And now if I have to write it in terms of real and reactive power, that will be S is equal to 800 megawatt plus 539.672 J MVR. So this is your real power and this is your reactive power, right? This is P and this is Q. Now if you have to calculate the real power from this one, so it is P is equal to 965.1 cos 34 degree, and for Q it is 965.1, it is sin 34 degree. So after solving this you have 800 megawatt, and for reactive power it is 539.672 J. So this is the second part that you have to solve, and the last thing that you have to calculate is voltage regulation. So from the formula of voltage regulation, VR is actually equal to V no load minus V full load over V full load into 100. So now we know the formula for the sending end voltage Vs. It is actually equal to cos beta L VR plus JZC sin beta L IR, and V no load is actually the receiving end voltage when IR is equal to 0, and V full load is actually the VR value that we already calculated. So if I have to find V no load, what I have to do, I have to take IR equal to 0, and then Vs is equal to cos beta L V no load. So I have replaced VR with V no load. So because IR is equal to 0, so I'm just replacing VR with V no load. So V no load is actually equal to cos beta L over Vs. We know the value of beta L, we also know the value of sending end voltage. So after putting the values, which are 356.53 over 0.9295 is equal to 383.57 kilovolt, and all these values are actually the magnitude, right? So that's why I'm only taking the magnitude of Vs. Okay, now at full load, this was at no load. V full load, we already know that, which is VR. So taking the magnitude of VR, that would be 288.675 kilovolt, and putting these two values in the voltage regulation equation, that will become 383.57 288.675 divided by 288.675 into 100. So that is equal to 32.87%. So this is your voltage regulation for the given example. In this lecture, we have covered the surge impedance loading and also the Ferranti effect. And in the last portion, we have solved an example in which we have to find out different quantities for the long transmission line, which is a lossless line. And the phase constant, we have to find surge impedance and velocity of propagation and line wavelength. And in the second portion of the question, we had to find the sending end quantities, the sending end voltage, sending end current, and also the sending end power. So we have calculated all those, and in the last part we have to calculate the voltage regulation. We use the formula of the voltage regulation, and to find the voltage that is at the receiving end without any load attached to that, we have taken IR is equal to 0. The equation became Vs is equal to cos beta L V no load. So this is actually the receiving end voltage, but I just replaced it with no load because IR is equal to 0, and then we calculated both the voltages, V no load and V full load, and the voltage regulation value that we got out of that was 32.87%.